Right, year 13. Like some sort of genius, I managed to mess up recording me doing this. So I'm just going to talk you through these notes here with them already filled in. So we're on page 188. So make sure you fill in your notes as we go through and keep pausing and filling in and all that kind of carry on. Now, this is the last little bit of our momentum section. And all we need to do is learn about elastic and inelastic collisions. So whenever two bodies collide, then from the principle of conservation of momentum, the momentum before will be equal to the momentum after. And that just means that the momentum, or we would say that the momentum is conserved for the collision. And conserved just means it's the same before and after. Now, the total energy is also going to be conserved, so the total energy before is going to be equal to the total energy after, and the reason for that is because of the principle of conservation of energy. So this is the one that everyone remembers. Energy cannot be created or destroyed, only changed from one form to another. So the total energy before a collision is going to be equal to the total momentum after, but the total kinetic energy isn't always going to be the same before and after. So if we have two things and they collide, then the total kinetic energy before, so whatever kinetic energy these two things had before, say they were moving towards each other, that isn't necessarily going to be the same, or the total kinetic energy afterwards. And if the kinetic energy is conserved or not is what determines whether a collision is elastic or inelastic. So momentum and total energy are conserved in all collisions, and you end up using this in calculations fairly regularly. But the total kinetic energy of the system isn't the same before and after. Okay, so let's have a little look at this table. So we've got the three different collision types here. So the elastic collisions, they're highly unrealistic, okay? But we've got elastic collisions, inelastic and completely inelastic, and we'll go over what the difference between these two are. So in every single type of collision, momentum is always conserved. In every single type of collision, total energy is always conserved. But the kinetic energy isn't always conserved. If it is an elastic collision, the kinetic energy is conserved. Now, the description for that, in reality, an elastic collision can only really occur on an atomic scale. So, and our example of that is the collision of two ideal gas molecules. Now, if you do chemistry or did chemistry, you maybe already know what I mean by that. Everyone else, don't panic. You learn about ideal gases next year, but basically ideal gases act as if there's no forces acting between them. So there's no electrostatic forces or no nuclear forces, anything like that. And they also act as if collisions take zero time and as if the molecules themselves have zero size. So they're sort of a made up thing, because we like that in physics, don't we? But technically speaking, that is what an elastic collision is. In reality, it won't happen that often. Inelastic, kinetic energy is not conserved. So in an inelastic collision, it's a much more realistic situation, and that involves kinetic energy being converted to heat or sound. So that is what happens in real life. So the example that we put down for that is just a tennis ball hitting off a racket. If it's completely inelastic, again, kinetic energy not conserved, and in a completely inelastic, the loss of kinetic energy is really a lot. So, and that tends to mean the two things have stuck together. So something has like fired into something else and stayed there. So like a bullet into a sandbag is the example that we've put down for that one. Okay, so a really big loss in kinetic energy, generally whenever the two things stick together, we would call completely inelastic. Now, the way you're most likely to have to use this information is to determine whether a collision is elastic or inelastic. So to do that, all you need to do is check and see, is the kinetic energy before equal to the kinetic energy afterwards? So that's all this is. If you remember from GCSE, the kinetic energy equation is a half mv squared. So say this was our two things colliding together, if they're going towards each other. This one will have a kinetic energy before and this one will have a kinetic energy before. So that's just adding the two kinetic energies together, and we've used U because it's the initial situation, it's the before. So whenever they collide, and then say once they've collided they go apart again and they move apart, then they're going to have a kinetic energy afterwards, each of them. So we just add the two befores together, see what you get, add the two afters together, see what you get, and see if they're the same as each other or not. Okay, so our example for this is a car of mass 1,200 kilograms moving at 10 meters per second collides with a stationary car of mass 800 kilograms, and the two cars stick together. And then you're asked, is the collision elastic or inelastic? So to figure out if it's elastic or inelastic, all we have to do is see, is the kinetic energy before equal to the kinetic energy afterwards? Now for the before situation, we do have enough to figure out the kinetic energy. We know the mass and the speed of this one that's moving. The other one doesn't have any kinetic energy, so we're fine, we can figure out the kinetic energy. But it hasn't told us what speed the two cars move off with, so we can't figure out the kinetic energy after just yet. Now the fact that they have stuck together implies that this is a completely inelastic one, so it isn't going to be conserved. So we sort of already know that's going to be the case, but you would obviously have to do the maths to prove that. Okay, so let's look at the solution. There's room for your solution at the top of page 189. Right, so we've just said that we need the velocity afterwards to figure out the kinetic energy after. So we can use the fact that we know the momentum is going to be conserved to get that velocity afterwards. So we can say the momentum before is equal to the momentum after. Whenever I was writing this, I stupidly forgot they were both two cars, so the way I've labelled them are the initial momentum of the car that's moving, MU, I've used MU, and then MU for the stationary car, that's what the EST is all about there. And the momentum after, because they stick together, we can just call that all one, MV. Now, the momentum of the one that's moving before is going to be its mass, 1,200, multiplied by its velocity, 10. The one that's stationary has no velocity, so it's just 0. And afterwards, don't forget to add the two masses together because they're stuck together, so it's the 1,200 plus the 800. So that's where that 2,000 has come from. And then just working down through that, you end up getting a velocity of 6 meters per second afterwards. So now we've got our velocity afterwards, we'll be able to figure out our kinetic energy afterwards. So, kinetic energy before, half mv squared, I've just called it u to keep myself sorted in terms of that's the initial, so a half mu squared. The only one that's moving is that 1,200 kilogram one, so that's the mass that we use because it's moving at a speed of 10. If the other one was moving, then you would calculate the kinetic energy of it and add the two of them together to get the total. So we've ended up getting the kinetic energy before to be 60,000 joules. The kinetic energy after, now because they're stuck together, we've got a half mv squared. The total mass is 2,000 and the speed is the 6 that we had figured out up here. So that got us a kinetic energy afterwards of 36,000 joules. So, because these two numbers are different from each other, because they're not the same, kinetic energy has not been conserved, so it's an inelastic collision. And I've just made an extra wee note there that the kinetic energy must have been converted to heat and sound. The total energy of the system hasn't changed, it stayed constant. So there must be 24,000 joules of energy has been changed into heat and sound. Okay. So that is momentum finished, and what I need you to do then for the rest of the week are the momentum exam questions. I'm not going to ask you to bother doing these exercises. If anyone wants to do them, I do have my solutions that I can upload for you if you want. But there's a bunch of them, they're just unnecessarily awkward. There's some of those ones that some of the wee maths geeks might like, and that is a bunch of you, isn't it? If you admit it, go on. So I can upload my answers to those, but I wouldn't worry about them. I would much rather you did the exam questions because they're more realistic to the ones you're going to get asked. Okay, so that's it for momentum. Just one topic left. See you next time. Bye.